Good morning, everyone. In the last session, we have seen the use of advanced universal functions to perform aggregation operations on one-dimensional, two-dimensional, multi-dimensional. And when you are performing aggregate operations on different dimensional arrays, you encountered certain issues with size and shapes of different dimensional arrays. To address this, a NumPy arrays gave us the feature called broadcasting. Computation on arrays using broadcasting will help us to normalize the arrays to apply various operations. We saw in the previous section how NumPy's universal functions can be used to vectorize operations and thereby remove slow Python loops. Another means of vectorizing operations is to use NumPy broadcasting functionality, where the broadcasting is simply a set of rules for applying binary universal functions such as addition, subtraction, multiplication, and so on arrays of different sizes and different dimensions. Recall that for arrays of the same size, binary operations are performed on an element by element basis. So here I just took two one-dimensional arrays and then performed simple addition. Now, broadcasting allows this type of binary operations to perform on arrays of different sizes. For example, we can just as easily add a scalar to an array A. A is a single dimensional array and we are trying to add a scalar value 5. But 5 is not a simple 5. We can think of this as an operation that stretches or duplicates the value 5 to the size equal to A, such as an array with our elements 5, 5, 5, and adds the results. The advantage of NumPy's broadcasting is that this duplication of values does not actually takes place, but it is a useful mental model as we think about broadcasting. We can simply extend these two arrays of higher dimension. Observe the results when we add a one-dimensional array to a two-dimensional array or higher dimensional arrays. Now let us see. So I have one-dimensional array and a two-dimensional array. M is a 3x3 matrix, and whereas A is a one-dimensional. If you want, you can just take the shape, print A dot shape. Okay, print M dot shape. Now you observe dimensions are different. Okay. Usually, performing operations on different dimensional elements is a critical calculation or critical application. But in NumPy, you can just do like this. When you add A to M, it's very simple. But whereas my A is only having 3 columns, I mean it's a row array, row matrix, whereas my M is 3x3 matrix. When you add it, you will be adding to all the columns. row wise. Here the one-dimensional array A is actually stretched to the size of two-dimensional array. So after stretching, you can observe the shapes will change. I mean to say, A also become 3 by 3 matrix. There are certain rules in order to match the dimensions of both the arrays before applying universal functions. Let us see, these examples are relatively easy to understand. More complicated cases can involve broadcasting of both the arrays. For an example, let's take two arrays. There's a row matrix and column matrix. A is a row matrix, whereas the B is a column matrix. Now, if you perform A plus B, what is expected? Neither a row matrix nor a column matrix, but it is row into column matrix. There are 3 rows and 3 columns. Obviously, when you perform addition, you are going to get this is the result. But how it is possible? Just as before, we stretch the size, the dimension of an array to match the dimension of the other array. Required certain measurements. Here, we have stretched both A and B to match a common shape. What is that? A is having 1 row, 3 columns. B is having 3 rows, 1 column. Then this one must be stretched. I'm to say A dot shape, right? B dot shape. If I don't use print, what happens? Prints only the last code snippet, output of the code snippet. Now you can observe. Say it is 1, 3 and 3, 1. So where 1 must be stretched to 3 in both the array sizes. That's the challenge. Now you can observe here in this diagram. When I apply A plus 5, A is a row matrix, whereas here 5 is a scalar. When you perform addition, you are able to get this result. But you can see internally the low focused cells are actually imagined, but they are not real. So it is propagated the value 5 into the other dimensions to match the dimension of it. So that the A and this 5 is also of same dimension, so that the addition is assumed possible for using universal function. If you take 3, 3 and then only 1, 3, now this 1, 3 is supposed to be stretched to match with the dimensions of 3, 3, 3 into 3. Then that's what, there is only 1 row. It is stretched to 3 by adding 2 more rows, the same values. Now both become 3 by 3 matrices, and performing universal function addition is pretty possible. Similar to that, if I use a column matrix 3, 1, a row matrix 1, 3, now both ones are stretched to 3 in both the arrays to match the dimensions of one and another array. So the less focused cells are imagined or stretched to match the sizes of the other array dimensions. This is exactly what is the imagination of stretching to meet or to match the sizes of the other higher dimension arrays, called as a broadcasting. The light boxes represents the broadcasting values, as I told you. Again, this extra memory is not actually allocated in the course of the operation. As I told you, it's only an imagination, but it can be useful conceptually to imagine that it is. Let us see the rules of broadcasting. Apply universal function. Broadcasting in NumPy follows a strict set of rules to determine the interaction between the two arrays. Rule 1 says the two arrays differs in their number of dimensions. The shape of one with a fewer dimension is padded, stretched, with ones on its leading left side. It is stretched with ones on its leading left side. Leading side, that is left side. Let us see this and then come back. In example 1, let us see adding two-dimensional array to one-dimensional array. I've got M is a two-dimensional array, A is a one-dimensional array, whereas performing addition between these two. Let us see the performance of addition of these two. Now you can see, to understand, my M is 2 into 3 matrix, whereas my A is 1 into 3 matrix. Okay, the sizes doesn't match. In this case, as per rule 1, what rule 1 says? When the dimensions are not matching, then you have to pad 1 to the leading side of the lower dimension array. What is the lower dimension? This is the lower dimension. What I have to do is I have to add 1 at the beginning of shape. So that's how now my new shapes becomes 2 into 3 and 1 into 3. All right. Still, these two are not same. Then what rule 2 says? Rule 2 says the shape of the two arrays does not match. Right? It is 2 into 3 and 1 into 3 now. They do not match in any dimension, isn't it? But they are matching. Anyhow, they are matching in one dimension, that is 3. But if they do not match in any dimension, they arrive with the shape equal to 1 in the dimension is stretched to match the other shape. If there is a one dimension, then if there is a shape 1, then the column or row, that is supposed to be stretched to match with the shape in other array. That's what 2 into 3 and 1 into 3, where this is not matching. Okay, this one is not matching 2, then you can say 1 to since both become 2 into 3 matrices. The shapes of both the arrays are now matching. All right. Now simply this is how internally happen, and when you perform M plus A, it is a simple addition now. Understood? what you can do is simply print M for easy understanding, print A for understanding. Don't expect the shapes are reflected on original data. The shapes doesn't change permanently, but it is only an imagination, logical imagination for us to understand how the data is propagated when you are applying universal function operations, right? So an example, let's take one more example. Okay, let's take one more example. In this example, I've taken the same example like now, a row and column matrix, right? A is a column matrix and then B is a row matrix. Then I wanted to add. Now let us observe carefully here. My dimensions are 3 into 1 and 3. So now as per rule 1, I am supposed to add 1 to the lesser dimension array to its leading side. So then in this case, this is a 2-dimensional, this is a 1-dimensional. Then I am adding 1 to the left of this. 3. Then it become A become a 3, 1 and B shape become 1, 3 after adding 1 to the leading left side. As per rule 2, now none of them are matching. And what we do? We stretch 1. Whether it's the left side or right side, it doesn't matter. If there is a 1 dimension, that will be stretched to match with the shape in the other dimension. Okay, or other array dimension. Now I can say this one has to be stretched or padded to match this 3. So it becomes a 3. Similarly, this one is supposed to be stretched to shape in another array. So both become 3, 3, 3 matrices. Right? Now, simply if I perform addition, that's the reason why you get a 3 into 3 matrix. But if you test the shapes again now, you can't see the same with 3 by 3. A dot shape, B dot shape. Don't expect it to happen permanently. As I told you, it is only a logical imagination for we to understand how the data is propagated to apply universal functions using NumPy feature called broadcasting. Okay. Right. Now, let's take one more example and then close it here. Broadcasting example 3. And the 2 arrays are not compatible. Suppose if I take 2 arrays, M is 3, 2, and then whereas A is taken as a row single dimension, I wanted to perform addition. In this case, what we'll do, we'll apply rule 1 when the dimensions are not matching. Then we'll add 1 to the leading side of the lower dimension matrix. So that's how it becomes 1, 3. Now still it's not matching, right? Still it's not matching. What we do now? We try to add, as per the rule 2, we try to stretch 1 to the size of the other dimension matrix. So 1 will be stretched, then it become 3 comma 3. A shape become what? 3 comma 3. But now you observe carefully. In the previous example, we could able to form 3 comma 3 and 3 comma 3 because it was 2 comma 3. But in this case, it is 3 comma 2. Shape of M is 3 comma 2, whereas shape of A is only 3. But with the rule 1, we could able to add 1 in the leading side of the lower dimension array, and it become 1 comma 3. And since the dimensions are not matching, then we apply rule 2, and then 1 is stretched to match with the shape of the other dimension, then 1 is stretched to 3. It become 3 comma 3 and M is 3 comma 2. Still, these two are not matching. In this case, we will apply rule 3. What rule 3 says? Rule 3 says, if in any dimension the sizes disagree and neither is equal to 1, an error is raised. Okay. This example 3. Now you can observe here neither. See, this 3 and 3 is matched, and then 3 and 2 are not matching, and either of the 1 is not 1. Neither of the dimension is 1. Add it or to stretch it. There is no scope to stretch since there is no 1 after applying rule 2. Then simply it raises an error. Now let us try to apply addition between M and 2 matrix. Before it, you can simply print the values, otherwise shapes, sorry. Okay. Anyhow, shapes will not be reflected or permanently changed in the memory, as I told you. So what I got is, I got an error. This is rule 3. So simply to make you clear, once again, I'll just read out the rules we are supposed to apply under broadcasting for our universal function applications. In rule 1, if two arrays differ in their number of dimensions, the shape of the one with a fewer dimension is padded with the ones on its leading left. Still, if the sizes are not matching, if one of the size of a shape is 1, then you can add, you can stretch its value to match with the other shape dimension. Even after doing that, if the sizes are not matching and neither the dimension is equal to 1 to further stretch to match it, simply raise an array. So this is an internal arrangement provisioned by the NumPy library in the name of broadcasting to apply various universal functions on different dimensional data. Thank you very much for attending this session 6. So I suggest all the participants to practice more examples to better understanding the rules of broadcasting, how they are internally arranged to perform various operations on different dimensional arrays. See you in the next class.